Hello, this is Professor Gina, and I am going to talk about the polar equations of conic sections in this video. These problems are quite intense and lengthy, so this is probably going to be one of my longer videos. We learned about polar equations, and then we also learned about changing between rectangular and polar equations a couple chapters back, and so this is sort of bringing all of those ideas together. There are a couple important ideas for us to have, and I put them here at the top of this page, which are the general equations that we will have for the conics. And then we have this variable called E, which is the elasticity, which actually tells us how close to a circle a particular conic section is, specifically in the context of an ellipse. And so we can see if E is equal to 1, we know that we're going to have a parabola. If E is a fraction, then we have an ellipse. And if E is greater than 1, we have a hyperbola. Also, I just put a note here down at the bottom that if the eccentricity is 0, then that means that we have a circle. For the first set of problems that I have, I'm going to follow this set of directions. I'm just going to make it a little bit bigger here. This set of directions that I've got down here, which is we're going to take an equation and determine which type of conic section it is, and then we'll figure out which direction the directrix is going. And some of that will be assisted by this table that's on the right-hand side. We'll kind of come to that as we need it. But just so that you know, even though we've only talked about a directrix in terms of a parabola, there's actually one in a hyperbola and an ellipse as well. It's just not part of the graph that we've drawn. All right, so for our first example, let's look at the equation r equals 1 over 1 plus cosine theta. And we know that what we want to do, remember r has to do with the radius of a circle, and then cosine would be the angle that's going around with different angle measurements. We know that we want the equation to look like the format of r equals E times some variable p. This is not the same p that we had when we were graphing conics before. It's just a different variable. 1 plus E times the cosine of theta. We know this is what the general equation should look like. So looking at this, it looks like we have E being equal to 1. Right, because we don't have any number sitting here, so E is equal to 1. So then that means that in the numerator we have E times P is equal to 1. I'm getting that from here, and since E is 1, that's going to tell us that P is also going to be 1. So in this particular equation, both E and P are equal to 1. All right, now, one of the things to note is that because E is equal to 1, looking at our table above, that means that we have the equation of a parabola. So this is going to be a parabola. That's answering the first part A. And then because it's a parabola, it's either going to be opening up, down, left, or right. And the way that we determine is based on the trig function that's given. Because cosine is related to our x values, that's going to always go left, right in the direction of x, where anything that has a sine in it is going to go up, down in the direction of y. So this is going to be a parabola that either opens to the left or opens to the right based on the fact that there's cosine in the equation. Now, how we tell is by looking at this table here on the right-hand side. So we've got a plus in the middle, and that helps us know that we have the directrix on the right-hand side of the focus. So in general, if we have something like this, the directrix on the right-hand side and the focus is here, that means that our parabola is opening up to the left, right? So that's answering question B. Question B was asking us where the directrix was. The directrix is a vertical line. And it's going to be 1 unit to the right of what in your book is called the pole, or we know it as the focus point. Now that 1 comes from the variable p, and so that means that this distance here is going to be p equal to 1. And we know that the vertex is going to be in the center of those two, in the center of the focus and the directrix in the middle of them. So part C is to find the vertex. So the vertex is going to be found when theta is equal to 0. Because we're starting on the axis, there's another axis, I'll just draw it like here. And this one's going to end up being I think the axis is going to end up being like around here as our 2 axes, somewhere around there. Remember that when we have polar graphs, we're going around and around, and because we're at the horizontal, that's going to be when the angle is equal to 0. So I'm going to plug 0 back into my original equation. So I'll plug in, our original equation was r equals 1 over 1 plus cosine theta. When we plug 0 in, we get that r is equal to 1 over 1 plus, now the cosine of 0 is 1, so that's at 1/2. So that means that the vertex is at 1/2, comma 0. And in this case, 0 represents an angle, and 1/2 is how far it is on the angle 0. So that means that this distance here, right here, this distance is 1/2, right? And then the last part, I think, was just to get a rough sketch of a graph, and we have one. You can go into Desmos and you can actually plug these equations in as you see them, and you'll get a graph that looks similar to what I've drawn here. All right, let's tackle another example. Let's look at the equation r equals 4 over 2 plus cosine theta. This is an equation that similarly has cosine in it. So that means that it's going to be either opening left, right, if it's a parabola or hyperbola, or it's going to be stretched with the major axis in the direction left, right, if it's an ellipse. We have to change this equation around a little bit to figure out what type of equation it is. Looking back at the original equations that we had, one of the important things to note is that we will always have a 1 in that first position there. So what we're going to do is change this equation to make sure that we have a 1 as that starting point in the denominator. So what I'm going to do is I'm going to divide the top and the bottom by 2. I'm going to go ahead and say I'm going to multiply by 1/2 on the top and 1/2 on the bottom, so that I can change that first 2 into a 1. So we'll have r is equal to 4 times 1/2 is 2, and I'll have 1 plus 1/2 cosine theta. All right. That means that E, which is sitting right here, is going to be equal to 1/2. And then I take what's in the numerator. The numerator is 2. E times P is equal to 2. We said that E is 1/2. So I'm getting that P in this case is equal to 4. Because E is equal to 1/2, going back up to our chart up here, when E is a fraction, that means that the graph we have is an ellipse. So we know that the graph is an ellipse. And the directrix is going to be 4 units. I think it's going to be to the right of the pole also because it's a plus. Let me just look up here. We're looking at this one right here. We've got cosine and we've got plus. So the directrix is going to be to the right of the pole or the focus point in this case. And P tells us how many units away it is. So part B is the directrix will be 4 units to the right of the pole or focus point. Okay, the next thing that we want to do is find the vertices. We know that this is going to be an ellipse. It's going to look something like this. Let's see, it's going to end up looking something like this. And we want to find the 2 vertices. And so the vertices are going to be at the places where theta is equal to 0, and then when theta is equal to pi, swinging all the way around the circle. So to find the vertices, we're going to let theta equal 0 and let theta equal pi in our original. So we had r equals 4 over 2 plus cosine 0. And then we'll have r equals 4 over 2 plus cosine of pi. Cosine of 0 is equal to 1. So we get 4 over 3. And then cosine of pi is equal to -1. So we're going to have 4 over 1, which is just 4. So the 2 vertices are at 4/3. That's how far we go out. That's what the radius is. And the angle there is 0. Again, that 0 is 0 in degrees. I'm sorry, in radians. And then the other vertex is at 4, pi. So the 4, pi is going to be this one. And then the 4/3 0 is going to be that one. All right. The directrix on an ellipse, there are 2 of them. One of them is going to be out here, and one of them is going to be out here. And remember that we have 2 focus points, right? So this will be one directrix, this will be a second, this will be like the first focus point, and this will be the second focus point. So that's where they are in an ellipse. Okay. Let's look at r equals 15 over 5 minus 10 sine theta. The first 2 examples that we did had a cosine. This example has a sine. So because sine is the variable that's related to y, we know that this is going to be a parabola that opens up down or a hyperbola that opens up down. Or if it's an ellipse, it's going to be stretched. The major axis will be going vertically. So similar to what we did in the last example, we need to change that first number in the denominator to a 1. So we're going to multiply everything by 1/5 over 1/5. And so we get that r is equal to 3 over 1 minus 2 sine theta. we know then that E is equal to 2. And then E times P is equal to 3. And again, that's coming from the numerator. So I have 2 times P is equal to 3. So P is equal to 3/2, which is greater than 1 when, E is greater than 1. So that means that we know we have an ellipse. We know we have a hyperbola because E is greater than 1. This is a hyperbola because E is greater than 1. And it's going to open up, down. So let's look back at our table up here on the top. We've got a sign and we've got a minus. So that's the last category. So we have a horizontal directrix, which is P units below the pole. All right, so the directrix is horizontal. All right, so we know that our graph is going to look something like this. I'll just draw what it looks like and we'll talk about it in a minute. You can just look at Desmos to figure out what these look like. It's going to be something like that. To find the vertices, now here we're looking at different angles because we know that the vertices are going to be related to angles coming from here and angles coming from here, right? So this is pi over 2 and this is 3 pi over 2, right? When we're swinging around the unit circle like this, right? So remember our polar graphs. All right, so for the vertices, are at theta equals pi over 2 and 3 pi over 2. So taking our original equation, we're going to say R is equal to 15, 5 minus 10 times the sine of pi over 2. And R is equal to 15, 5 minus 10 times the sine of 3 pi over 2. The sine at pi over 2 is equal to 1. So here we have R is equal to 15 over 5 minus 10. That gives us R equals -3. Here we have R is equal to 15 over the sine of 3 pi over 2 is -1. So that'll be 5 plus 10. So we get R is equal to 1. So our vertices are at -3 pi over 2 and 1 3 pi over 2. So again, looking at the picture that we have, this value here is 1 3 pi over 2 because we're going in the direction of 3 pi over 2, which is down, and we're moving 1 unit. Whereas this value here is -3 pi over 2, because if you start at the direction of pi over 2, which is up, you're going to go the opposite way, which is that negative. So you're moving away from pi over 2, so it's going to be -3 down. So those are where those 2 points are coming from. And then again, the directrix for these, there are 2 directrix lines which are cutting through the middle here. And then the focus points will be on the interior like this. Again, you can go to Desmos and you can graph these to see what they look like. The next thing that we're going to do is we're going to go back and redo the 3 problems we just did. But what we're going to do is we're going to convert those previous equations to rectangular coordinates. They were given to us in polar, and we're going to convert them back to rectangular, which is what we're more used to seeing and what we saw in the conic sections problems that we had earlier in this chapter, in chapter 10. So I put up here at the top the equations that we use to convert between rectangular and polar coordinates, just to remind you. So what we're going to do is convert the equations to rectangular. So the first example that we had was r equals 1 over 1 plus the cosine of theta. That was the first example that we did. So what I'm going to do to get started is I'm going to clear that denominator. I'm going to start by multiplying both sides by 1 plus cosine theta, 1 plus cosine theta. And so I'll have r plus r cosine theta on the left equals 1 on the right. Now, I'm going to subtract r cosine theta from both sides. You'll see why in just a second. Because r cosine theta is one of our definitions. R cosine theta is the same as x, and so we can make a substitution there. So we'll say that r is equal to 1 minus x. And then r, we also have a substitution for that. R is the radius, right? And so r is the same as the square root of x squared plus y squared. We know that we're in rectangular coordinates when we've gotten rid of any r or any trig values, and we have just x and y's. All right, let's square both sides here to get rid of that square root sign. I did here 1 plus x, the quantity squared. And then I'm going to subtract x squared from both sides. And I've got y squared equals negative 2x plus 1. We already saw this in the previous example when we did this to start, but this is a parabola. I know that because only one of the variables is squared, and it's a parabola that's either going to open left or right because y is the variable that's squared. And in fact, it opened to the left, and we know that because we've got a negative sign there in front of the x term. Now, also just to kind of tie up what we did in the previous example, we were looking at the polar version. If I rewrite this in the version that will let me see what the vertex is, I need to kind of modify what I have on the right-hand side. I'm going to factor the negative 2 out. And I have x minus a half. I would do negative 1/2 times negative 2. That'll give me positive 1, right? And so now I can see that the vertex in this case is 1/2 coming from the right-hand side and 0 coming from the left-hand side. This matches the vertex that we found when we were looking at this in terms of polar. So this is the rectangular version. The polar version is 1 over 1 plus cosine theta. Okay, let's do the second one. The second equation we were given was r equals 4 over 2 plus cosine theta. I'm going to tackle this similar to the way that I just did in the last one by clearing the fractions. So I'll have r multiplied by 2 plus cosine theta equaling 4. And then I'll subtract that r cosine theta from both sides. So this is the same as 2r equals 4 minus x, right? Because this part is equal to x. R, we know, is the square root of x squared plus y squared. And then I'm going to square both sides to get rid of that square root symbol. When I do that, I have to square the 2 and the square root symbol. So I'll have a 4 here in front multiplied by x squared plus y squared equals 16 minus 8x plus x squared. All right, so 4x squared plus 4y squared equals 16 minus 8x plus x squared. This is, let's subtract x squared. Actually, yeah. So I'm going to have 3x squared plus 8x. I'm going to move everything to the left. Plus 4y squared minus 16 equals 0. Because both x and y are positive, they have positive coefficients, I know that this is an ellipse. We saw that when we did this example before in polar. And we can find the center by rearranging this. The way that we would rearrange this is actually quite lengthy. I'm going to go through this, and this is sort of just showing you how having this equation in polar form is actually much easier than in rectangular form to find the two vertex points that, that we found previously. I'm going to go through this example now. So we're going to find the vertices. Okay. This is not what you're part of what's asked to do in this problem, but I just want to show you that we get the same answer, but why this process is much lengthier and the purpose behind using polar equations instead of rectangular. What we do is we group the x terms together and the y terms together, and we factor out the coefficient that's in front of the squared term so that we can complete the square. Oh, yeah, I'll leave that like that. And then we move any constant that has no variable onto the right-hand side. Okay. The middle term here is 8 over 3. Half of 8 over 3 is 4/3. We're going to square that and add it to both sides. So I'm going to put plus 16 over 9. But when I look at these, what I actually added was overall 16 over 9 times 3 is going to be 16 over 3. So I add 16 over 3 to the other side to keep it balanced. Then I'm going to compress what I have here. I've got 3 times the quantity x plus 4/3 squared. And then I've got 4y squared equals, you can plug this into a calculator and it's going to give you 64 over 3. All right. Now, because this is an ellipse, I need to have a 1 on the right-hand side. So what I'm going to do is I'm going to divide everything by 64 over 3. And again, you can plug these values into your calculator. 3 divided by 64 over 3. The way that an ellipse is written, we have those numbers down in the denominator. And so that would be This becomes 64 over 9. This becomes 16 over 3, and then I have a 1 on the other side. So A in this case is equal to, remember we take the square root of the number that's in the denominator. A is equal to 8 over 3. B is equal to 4 over the square root of 3, taking the square root there. The center of this is at -4/3, 0. Again, I'm getting that from this, the numerators here, and what's being subtracted from the x and x squared and the y squared terms. Now, I know that this is elongated to the right and to the left. And so to find the vertex points, I'm going to add a to the x term. So the vertices are -4/3 plus 8 over 3 going to the right, and then also -4/3 minus 8 over 3 going to the left. This gives us 4/3, 0. And -12 over 3 is -4, 0. Now thinking about, these are rectangular coordinates that we've been given, right? So -4, 0 is here. 4/3 is going to be about here. In polar, this equates to 4/3, 0 being the angle, and this equates to 4, pi, right? Over here, the angle is pi, and we're moving 4 in that direction, so that negative number goes away. These two vertices match with what we found when we did the same problem in polar, and it was a lot less work. So that's the benefit of using polar rather than rectangular. All right, we have one last example to tackle here for changing into rectangular coordinates. The last one that we had was r equals 15 over 5 minus 10 times the sine of theta. We'll rearrange this to be r times that denominator we'll multiply that out. And then I'm going to move that second term over to the right. So 5r equals 10r sine theta plus 15. Now r sine theta, or just this part, is equal to y. So I have 5r equals 10y plus 15. Let's divide everything by 5. R equals 2y plus 3. And r is the square root of x squared plus y squared. So we can make that change. So I've got, and then I have to square both sides, right? So I've got x squared plus y squared equals 4y squared plus, I multiply these two things together and double it, so that'll be plus 12y and then plus 9. Right, I'm going to move everything to the left. I'm going to have x squared minus 3y squared minus 12y minus 9 equals 0. I know that this is the equation of an ellipse, or sorry, a hyperbola, because there's a minus sign in the middle of the x squared and the y squared terms. And that matches up with what we had before. We can also go through the process of completing the square, finding the centers, and finding the vertices, but the process is lengthy, just like the one that I previously did. So I'm going to skip that part for now. All right, in this last set of examples, we are going to be given the eccentricity and also the directrix, and we're going to come up with the equation. I put some of the information that is helpful for us, that table that lets us know sort of where the directrix is related to what type of equation it is. And here I also put a picture that shows, we talked about for a parabola that the directrix is below the vertex or on the opposite side of where the focus point is. But here I put a picture of an ellipse and a hyperbola so that you can see where they are as well. All right, so let's say that we're given the eccentricity is equal to 2 and the directrix is the line r equals 3 cosecant theta. Well, first thing we know is that because this has eccentricity of 2, it's going to be a hyperbola. And we can rewrite the directrix in a format we're more used to seeing. We want to put it in terms of sine and cosine, right? So let's rewrite this as 3 over sine theta. Now this is the same as r sine theta is equal to 3, multiplying both sides by sine theta. And we know that this is the same as the same as y. So y is equal to 3. So we know that this is a horizontal line. And since it's a hyperbola, we think this is going to be opening up, down. So it's going to be one of the equations that has sine in it, right? So looking back up at our equations here, the directrix is going to be either above or below the pole. Hang on. Let me pause for a second. All right, sorry, I just had to pause for a second. So since it's a positive number, we know that it's going to be, we're looking at the 2 down here on the bottom, we know that it's going to be above because it's positive, and so we're going to use this first equation with a 1 plus e sine theta. So we know the general equation is going to be r equals e times p over 1 plus e sine theta. We know that p is going to be 3 because that's how far the directrix is away. So r is going to be e, they gave us as 2. 2 times 3 over 1 plus 2 sine theta. So our final answer will be 6 over 1 plus 2 sine theta. All right, second example. We're given that the eccentricity is 2/3, and the directrix is the line r equals negative secant theta. Changing that into sine cosine, we'll have r is equal to -1 over cosine theta. Multiply both sides by cosine theta, so r cosine theta is equal to -1, or x is equal to -1. So this is a vertical line. And because that's a negative number, it's going to be to the left of the focus point or the pole. And so we're looking at the second equation down, right? The second equation down that has a minus sign and that has a minus sign with the cosine. So that's the general equation that we're going to use. So our general equation will be R equals E times P over 1 minus E cosine theta. E they gave us as 2/3. P is, we're going to plug in 1, not -1, because it has to be the distance. And then we have 1 minus 2/3 cosine theta. So that is R equals 2/3 over 1 minus 2/3 cosine theta. I'm going to multiply everything by 3 to get rid of those fractions. Let's multiply by 3 over 3. So that gives us R equals 2 over 3 minus 2 cosine theta. Again, what we're doing is when we find P, that's just telling us the distance from the focus point or the pole to the directrix. And then whether it's positive or negative just tells us which side it's on, whether it's on the left or the right, up, below, or above. But distance is always going to be a positive value. Okay. Let's do one more like this. Let's suppose that the eccentricity is equal to 1 and the directrix is 4 secant theta, or R equals 4 over cosine theta. So R cosine theta is equal to 4, or X is equal to 4. So this is a vertical line, and it's going to be to the right of the pole. I think because E is equal to 1, this is a parabola, right? And so the general equation that we're going to use is R equals EP over 1 plus E cosine theta. E is 1, P is 4, so we're getting 4 over 1 plus cosine theta. All right, that is the end of the example problems that I have. If you have questions, send me an email and have a great evening.